Hi everybody, so now I'm going to introduce the terms that we're going to see for chapter 20, which this chapter deals with light. So the first term is going to be the speed of light. And this is going to be a constant. C is going to equal 3 times 10 to the 8 meters per second. And then we're going to see the term frequency again. And frequency is the variable lowercase f measured in hertz. We're also going to see wavelength again. And that's the Greek letter lambda measured in meters. And distance, x measured in meters. Time, t measured in seconds. And energy, E measured in joules. And there's going to be a constant, which is called Planck's constant. And it's going to be the variable h, and it's going to equal 6.62 times 10 to the minus 34 joules times seconds. And the equations that we're going to use for this chapter is going to be the speed of light is going to equal the frequency of light multiplied by the wavelength. And the speed of light is going to equal distance divided by time. And energy of light is going to equal Planck's constant multiplied by the frequency of light. So this concludes the introduction to the terms. Next we'll look at the concepts for chapter 20. So this is going to be the first lecture for chapter 20 on light. So what light is, well, let's look at the sun. So light is a wave, but it's a specific kind of a wave. So light from the sun is going to travel in this direction, to the right. And there's going to be a wave. So part of the wave is going to vibrate up and down. But there's going to be another part of, there's going to be a second wave, and this wave is going to travel into and out. It is going to travel in and out. So here, these two components, the first component, you find that it's an electric field. And the other component, the one that travels in and out, is going to be a magnetic field. So light is part of a broader spectrum called an electromagnetic wave. But you still have the same components. You have the electric field and the magnetic field. They both vibrate with the same frequency. So I'm just going to show the electric field just to make it simple. So this electric field vibrating up and down. It's going to vibrate up and down with a specific frequency. And it's also going to have a specific wavelength. And remember, wavelength is just going to be the distance from the top of one wave to the top of another wave. So this is going to be the wavelength of light here. So the other part is the most interesting property of light is that in a vacuum, all light travels at the same speed. So whether you have visible light, or even if you have, well, actually, let me make this the scale here. So light comes in different varieties. You have, for example, radio waves. They have long wavelengths. And then you have visible light that tend to have shorter wavelengths, all the way down to X-rays that have a really small wavelength or a high frequency. So electromagnetic waves, they have different properties because they have different wavelengths and frequencies, but something is the same for all light. and it's the speed of light. So all light, or all electromagnetic waves, no matter what their variety, they all travel at the same speed. So the speed of light is a constant of nature and is equal to 3 times 10 to the 8 meters per second. So if we go back to the last chapter, light is a wave, and in general, the velocity of a wave is equal to, be clear here, so here, the velocity of a wave is always equal to the frequency multiplied by the wavelength. But for light, that velocity is a constant, and it's just that value c. So here, this is an equation that describes if you know the wavelength of light, you can use this to get the frequency, and vice versa. So this next picture kind of gives you a clear idea of what I mean by an electromagnetic wave. So you have an electric field that vibrates. Actually, let me do the simulation first, and then I'll review that. This simulation is going to help us to understand what light is and why we call it an electromagnetic wave. And what you notice is that there's an electric field that vibrates side to side, and at the same time, the electric field is going to be the orange line that vibrates side to side. But at the same time, there's this blue line that vibrates up and down, and that blue line, that's the magnetic field. So because light is a combination of two things, an electric field that vibrates side to side and a magnetic field that vibrates up and down, or really they're all just perpendicular to each other, so we call that an electromagnetic wave. The next thing to understand is the relationship between frequency and wavelength. So let's just start with the high frequency. And as you notice, as I increase the frequency, the slider, the wavelength gets smaller. So the bigger the frequency, the smaller the wavelength. And you can see it here. This wave vibrates very fast, relatively fast, and the wavelengths are pretty short. And let's look at the other case. So now I'm going to make the frequency smaller. And as you notice, the wavelength gets longer. So this is probably going to be good enough here. And so you notice here, it vibrates more slowly. It has a smaller frequency, but the top of one wave to the top of another is longer. So for all waves, in this case here, electromagnetic waves, the bigger the frequency, the smaller the wavelength, and vice versa. This computer simulation is going to help us understand the relationship between wavelengths of electromagnetic radiation and the specific kinds of electromagnetic radiation. So here you're seeing something that has a high frequency or a short wavelength. And let's see what happens if I lower their frequency. So as I lower their frequency, you notice here that this is getting more towards the violet part of the spectrum, and now this is getting towards blue, green, and then now you have orange, and now you're at the infrared. So what you notice is that the wavelength gets longer and the vibration gets smaller. So the longer the wavelength, the smaller the frequency. So here again, you see here, you have a long wavelength and the frequency is smaller. And if you go down to radio, it has an extremely long wavelength and a short frequency. So let's work it the other way then. So here, I'm going to make the frequency smaller, and the wavelength is going to get long. I'm going to make the frequency higher, and the wavelength is going to get smaller. So we're going to increase the frequency. We're going to infrared. This is invisible. And you notice the frequency is going to get higher. It's going to vibrate faster, but as it does, the wavelength gets shorter. And green and blue. So something else to notice here is that red light has a longer wavelength and a smaller frequency, and blue light has a higher frequency and a shorter wavelength. And now we're at the ultraviolet and all the way over here to the extreme ultraviolet. So the basic relationship is that the higher the frequency, the smaller the wavelength, and they're opposites to each other. we're going to continue. This is going to be the second part of the lecture for chapter 20. And this is picking up from where we left off before, that we said that all light travels at a constant speed, which is going to be 3 times 10 to the 8 meters per second. So given that, you can actually figure out how far things are, and you can measure distances. And the way that it works is this. So if you have a flashlight, and then this is your eye here. Oh, I'll just do an eye. If you want to figure out how far you are from the flashlight, all you have to do is just turn, like somebody turns on a flashlight, and you just have to wait to figure out how long it's going to take for the light to reach your eyes. The reason why is because everybody's going to measure the same speed of light. And if you know the time, then you can just use this equation from chapter 3, that velocity is going to be distance over time. But specifically for light, it's going to be the speed of light is going to equal the distance traveled over time. So then you can use this equation here to figure out, if you know how much time goes by, how far light travels. But really the main application is not just one way, but you actually use relays. So let's say that you want to figure out actually let's do it this way. Let's say this is the bottom of the ocean here. And then you have a boat on the surface of the ocean, and you want to figure out how deep the boat is. You can use a signal. So you can send out some kind of a radio wave, and you'll send out so the radio wave is going to travel down to the bottom of the ocean at the speed of light, and it'll come back upwards also at the speed of light. So if you measure the time for the light to leave and to come back, you can figure out how deep the ocean is. Or in this case here, I'm just going to call that distance x. So in this case here, the speed of light, or the velocity, is going to equal the distance traveled, but the distance traveled was x one way down and also x again upwards. So it's going to travel a distance of 2x divided by time. So you can use this equation here to actually measure distance if you send a signal, if the signal travels back and forth. So an application of this is in medical equipment. So let's say if you want to figure out how thick a vein is, and here this uses sound. Sound works the same way because it's a wave. So you can have, just pull this one up here. So you can have an instrument, and the instrument is going to send out a pulse. And the pulse is going to go back into the instrument and the receiver. And if you measure the time between the signal being emitted and the signal being transmitted, and also if you know the speed of, in this case here, the speed of sound through tissue, you can use the same equation. It'll be the speed of sound is going to equal the distance traveled, but it's going to be a round trip, so distance to and then distance back. So it'll be 2 times x divided by the time. But it's the same basic equation. And this chart here gives you a list of the speed of sound in different, in bone and tissue. So this would be something that you can use to figure that out.